recording now. All right. So we had something like called spam-based. Like we transformed it to .csv, which is our data set, our main data file, which shows. Just want to do a quick overview. Every column was is showing a feature for an email, for a text email. For example, the frequency of some words, some specific words. And finally, what was the last column? 0 and 1s showing whether it's spam or not. Okay? Now, our task is to build a classifier using nearest neighbor classifier and test it on a test set, which we're going to split our data set to test and train, and then calculate the accuracy of our classification. Okay? Is the problem clear from last time? All right, let's do it. Let's do it really quick. Just going to open our studio and obviously close these tabs. They're confidential. Yeah. All right. We're going to do a sample. So the problem is, let's do the spam classification. Well, first of all, we're going to go to Files, for example, and then here I'm going to go to, I'm just going to navigate to the folder, and which we have. Well, I can't find it here, really. But anyway, here it is, spam base, for example. And then I'll click on Settings. Wait a minute. More, set as working directory. So I'm going to do that in order to access all of the files inside that directory without using the full path. Okay. Otherwise, you can access any CSV file or any text file that you have anywhere on your computer using the whole path. But right now, I can just use the file name. Okay. So the first thing is what? We need to import the CSV data, right? Which function, which library do we use for doing this? Exactly. Library utils is the first step I'm going to do in order to load the library that we need for read.csv, right? Okay, so I'm going to call it spam data, which is what? Read.csv of, I'm going to put the name base, exactly, spam base dot, so small b, right? .csv. All right, let me run this line and then run this. That easy, right? Just one line of code, and you don't even need to set anything else. You can simply just put the name here and let the other settings to be their default values. If I click on this, this is the database that we imported, right? You can simply see that it has 4,600 rows, and here's the data. Look at the column names. What are they? Nonsense, right? Do we care? No. Yeah. It's what? We're missing one row? Oh, okay. We're missing maybe the first row? Or? Okay, not a big deal. Yeah, exactly. We can just set the header to false or true. Yeah, that's right. But anyway, just want to make it, keep it simple as possible. Let's read the whole data. Well, we're just missing one record here. Not a big deal. Now, what I want to do is, what's the first step in classification? Split to train and test. Exactly. So I'm gonna use the word training instead of train because we use the function train. Right? I don't want to use that keyword, even though it's fine. But I'm just gonna use training. So training is what? Is spam data. Starting which rows? Starting from 1, end rows of spam data, and then by 2. And this is the testing data set. So it's spam data starting from 2, which is going to give us the second half, right? And this is like shuffled. I mean, another way to pick your train and test is you can shuffle your whole data set randomly and then pick the first 50% as train, the second 50% as test. doing this simple trick here, counting by 2, we're doing the same thing basically. We're just picking like random samples as train and random samples as test, right? Okay, what's up?
What if we don't want to split it 50-50? We want that 80.
Well, you can count. Well, you can just count another way. Like you can count by 3, for example, to pick like 30% of your data. Okay. You just have to make sure that your train and test do not overlap. That's a problem, right? So if you want to do like 30%, 70%, well, you can count by 3, but the problem is that if you want to count by 3 for the test, they will overlap finally, right? So in that case, the best way is to shuffle it randomly. You can use a random function in R to just shuffle them, yeah, and then pick the first 30% as your train, for example. But picking 50-50 is very common. People do that a lot, okay? It's very common. It's what? End row, exactly, yeah. So if we run this, we would get an error because we're writing end rows. All right, I'm gonna run this line and this line. Here we go. So we got the test and train set up and ready to go for the next step. All right, so what's the next step? We have to train our model. Is that correct? Very good point. So I'm just going to do it step by step. First of all, in order to train the model, which library are we going to use? Carrot. Perfect. All right, so I loaded the Carrot package here, and it's ready for use. Now, before renaming that column, I want to do the model, the train. Correct? Okay, what was the first input of train? The name of the column which you want to classify or predict. Okay, so what's the name of the last column? Well, we can set it up. Okay, so here we go. Let's say, so even before splitting it to train and test, we could simply say that spam data, the call name. So there's a function called call names, right? Call names of spam data. And how can I access the last one? Using a bracket. And then what should I put here? Well, you can either put n call, which is the number of columns, or you can just see what the number of columns is here. It's 58. So 58 is the last column. So I can put 58 here and set it to what? Spam. Okay? So if I run this line, see what happens. If you look at spam data, the last column is called spam. You could also use whatever name it had. It was like X, I don't know, some number. But just to make it clear, we're going to name that one column. And we don't really care about the other columns. That's the great thing about data science. I mean, a lot of times you don't even understand the data. You don't really know what's going on in those columns and how those numbers are measured. But you can build a very accurate model to classify spam from non-spam. Okay, now, so I'm going to do train and test again because we renamed the last column. Yeah, sure.
Let's say we were interested in a column that's like in the middle of somewhere.
Yeah.
Do we know the column number?
Yeah.
How would you classify it? Right now
If you want to access some of the columns in between?
Yeah, let's say.
Yeah, well, in that case, if you really care about what those columns are, you have to set up the column names at the beginning. So you can import, for example, the header names file, remember? The spam-based name file. And then put all of those names on the headers just to get some sense like what these columns are, or access them with their names. But in this case, we don't care what they are. There's some frequencies.
To include the first column to get 4601, was it header true or header false?
Header false.
You don't
Yeah.
actually have that one.
Yeah, exactly. Yeah, false. All right, so training and test, okay? Now, what's the next step? Model is train. What's the first input? Spam, tilde, dot, comma. What's the next input?
Data.
What is the data? Training, exactly. What is next? The method. What is the method? KK, NN, or KNN. K nearest neighbor. Okay? I'm going to run this line and see what happens. Now, there's one issue here. Let's see if it runs or not. It should give us some sort of error. The reason is, what is the type of the last column spam? What is the type of the data? It's numbers, right? It's not categorical because it's not strings. And we can print those values and see, oh, they're just numbers. Right?
So do you change this to as.character?
Exactly. So that's what we're going to see. It's probably mentioning the same thing. See, it's telling me that, are you looking for regression? Because you have numbers there. So why are you using k-nearest neighbor, which is a classification model? So now here's a quick point. Some of those models in the caret table are used for both regression and classification, okay? So if you use those models here, you're probably not going to get an error. Because if the code of ours looks at that last column and sees its numbers, it will assume this is a regression problem. It's not classification, okay? But here, k-nearest neighbor is only used for classification. And the code is telling me that, the compiler is telling me that, are you looking for regression? Because I see numbers there. All right, what we're going to do is, we're going to replace those numbers with strings. Okay? How can we do that? Simply by replacing it by characters. So here's what we can do. Here, right after we define the name of the last column, we can also change the type of spam data of spam to what? As dot character of spam data dot, dollar spam. You can use either as dot character or as dot factor. Both works. It's the same thing, basically the same thing. Okay, so I'm gonna run this again and then split my train and test and then run my model and see what happens. Take some time to run.
It's blue, not red.
Yeah, it's working. It's going to take some time because the reason is because the bottleneck here is the number of features. And we have a lot of features here. So we could
I have a question. So, do we use feature grid selections in real time most of the time? Or
exactly, yes.
if so, then
Also.
if we don't have the column names, how do we select those?
Well, again, we don't even in feature selection algorithms. Again, we don't really care what those features are, right? We're just going to pick feature whatever x270, for example, or column number 5, add it to our model, do the training, and see if the RMSE goes down or not, right? So that's the great thing about data science. You don't really necessarily need to understand all of the features and all of your data, what's going on exactly. You're just going to add it to the model and see if the RMSE gets better or not, right? If it gets better, well, that feature is helping you to build a more accurate model. Why? We don't know. Just go and ask the expert in that area, in that domain. Okay. But for modeling, again, we don't really look into what is behind the data. Not all the time. Sometimes for some justifications and some analysis, we may look into what the data is exactly. But especially in modeling, we don't really care, and especially in feature selection. Because there's a lot of times that you have. I mentioned. Like one of our recent projects that we're working on right now has more than 10,000 features. So if I want to sit down and look at what these features are one by one and what are their names, it's going to take forever. Just run a script, will automatically pick the best features for me and put them in the model. That's it. All right, what's next? Predict. So we're going to predict spam using the function called predict. What's the first input? Model. Second input. The new data, exactly. What is the new data? It's testing, right? Or we can say like new data equal to testing. Is this going to work? It will work. It will work. Last time I said that we have to remove the last column, okay? It will definitely work. But even if you don't remove the last column, it will automatically do it for you. Okay? So just dump in your whole testing data set, and it will ignore the last column, which are the labels, right? And the task here for this model is to predict those labels. So it's going to put it away. It's not going to look at it. Okay, so I'm going to run this line. See what happens. See? It ran. So predict spam is going to be what? It's going to be a bunch of 0 and 1s showing whether spam or non-spam for the test set. How many records? 2,300. Okay? So we got 2,300 labels and predict spam. We can even look into it. For example, predict spam. Oops. Oh yeah, we can. I can just print it here. I'm gonna print the first 10. Okay. See how it looks like. Here it is. So for example, we predicted that the first instance, the first email in the test set is spam. The second one is spam, and so forth. And this one is not spam. Okay. So we have like 2,300 labels in the predicted spam already. All right. What's the next step? The final step. Accuracy. We just want to see like how accurate these predicted spam labels are. And how can we do that? We're going to compare it with the actual labels in the test set. And we can do that. So the last part is calculate accuracy, which we can do by, I'm going to check if predict spam equal to what? Testing, exactly. Dollar spam. What is this guy going to give me if I run this? It's going to give me a bunch of true and falses. Like, it's going to give me 2,300 true and falses, showing me if every single label in predict spam is the same as testing spam or not. Okay? And we're looking for the true ones, the correct ones, the correct predictions. So how can I count the number of trues? And I'm going to use sum. So sum is going to give me, if I run this, take a look at it. It's giving me 2,084. So this 2,084 is telling me that 2,084 labels out of 2,300 labels were classified, were labeled correctly. Either spam or non-spam. All right, so what's the accuracy? It's going to be this number dividing by? Exactly. So we're just going to divide this by the number of rows of testing. Run, and here it is. It's 0.90%. Not percent, 0.90. 90%, right? So 90% accuracy for this classifier. So this means that if you just pick some random email and measure all of those 57 features, which were the frequency of different words and characters and capital letters, and then dump them in or plug them in into this classifier, into this model, with 90% accuracy, it's going to tell you whether that email was spam or not. Okay? Now, any questions to this point? Yeah.
I had a slightly different number, only just, I'm not sure. I got 2,073 for a spam count.
Okay.
I mean,
You're almost here. It's probably, I don't know, maybe your data set is, how many numbers we got? We got like 84, so there's like...
Oh, wait, no, it's because you got 4600. Never mind.
Okay.
I had the 4601. I corrected that.
All right, cool.
Never mind, sorry.
No worries. So,
I have two errors. So it says object model not found and then predicts found not found.
okay, so did you do the model equal to train? Did you run that line of code here? Because it's not finding this model. So it seems like it wasn't able to train that.
I did.
If you have to run it, I mean, does it run successfully or with error? It's probably running with error because you don't have the model defined, right?
I have it, but I think it's running.
Okay, I can check it offline maybe, or during the break. Right, besides this, before continuing this, how many people have to leave at 8:50? And is it possible that you stay longer after 8:50? I can continue the class until 10 if you want.
I
Can't stay until 9:30. 9:30? Is it fine for everyone? Or? Okay, we're gonna continue the class until at least one or two people say that, okay, I have to go. Okay? Let's do that. Or if you get tired, I mean, you can definitely just leave the class, yeah. Okay, yeah. All right, now, I'll look into that area, yeah, for sure. But at least, I mean, this code is working here, right? So any questions on this one here? So, no questions so far? All right, so for your lab work this week, I wrote a script which is able to read an email, a whole email, and calculate those 57 features automatically, okay? And I'm gonna send that script to you. It's an R script. All you have to do is you have to copy one of your emails, preferably a spam email, okay? Copy the whole text, dump it into a file called, I think, sample.txt, and then run the script. The script is gonna import that text of your email and will calculate all of those 57 features, and then plug that into this model and see if this model is going to classify your email as spam or not. Okay, so this is going to be like a real example, and it's one of your lab works. I mean, I'm just going to send you the script, and please do it because it took me like almost 5 hours to write that script. You'll see it's really crazy. What else? Any questions here? Yeah.
Yeah, we're doing with the converting as character.
Yeah.
So when I said the morning said something as for
Yeah.
factor and all, and when I was going to the help.
Yeah.
So it said that tilde dot is for regression. For classification, there was x, y, and two variables. Is there any other?
No. The only reason is because you didn't transform it into dot character as dot character. So it really doesn't have anything to do with the tilde. I mean, the tilde and the dot comes in regression and classification both. Yeah, there's no difference there. All right, any questions on this so far? Now, well, the next step is, I think it was probably part of the lab work. You can replace this nearest neighbor with some other models. Let's replace it with random forest, RF. See what happens. I'm going to run this. It's going to take a while. Oh, I think it's going to take forever. Yeah. And random forest takes a lot of computational time.
What exactly is random forest?
We can talk about random forest for like a whole session, what it is. But it's a tree-based model. What it's going to do, it's like a bunch of if and else's from top to the bottom, right? And then all of these like labels, predicted labels, are going to be at the leaves. So for example, it's going to say like if feature whatever is like greater than 50, go to the other branch and so forth. Okay, I can draw something on the board. Well, let's talk about it later. I'm just planning to put up some slides for random forest. Hopefully, maybe next time, and we'll talk about it. I mean, because random forest is one of the very, very useful models. Other than that, neural nets. Neural networks are one of the most useful methods and algorithms that are used right now, especially if you've heard about deep learning. A lot of deep learning methods are based on neural nets, like TensorFlow at Google, if you've seen this project. They're using neural nets, okay? Now, do you really have to know all the details about these models? No. You can just replace this with RF and use random forest. You can replace this with NN and use a neural net. That's it. But of course, it will be very useful and beneficial to have some insight about these models and see what they are. Like random forest is really interesting. I really like it. So I'll definitely talk about it next time. I'm just gonna put up some slides so it will be clear to talk about it because it's like based on like a lot of subtrees and then it does majority voting. If I want to draw it, it's gonna take a lot of time. I'm just gonna put up some slides hopefully next time. Okay. All right, this guy is gonna take forever. I'm gonna stop it. All right, any questions so far on the topic? All right, yeah.
For the course, I hear that if we just keep running and running and running, we'll find the ways to get the perfect answer. So we have to just kind of cut the
Yes, of course, yes.
Is there something we have to modify?
Well, there's like some default value for it, which will consider itself. But yeah, you can set some parameters. Like in random forest, the number of subtrees that it generates is a parameter. Okay, it's usually like default. It depends on the size of the data, but it's usually, I think the default is like 500. But if you want to do like 5,000, that's possible. I mean, you can just change the parameter. And it's going to take even longer, of course. Or if you want to do it like with less number of subtrees, you can also do that as well. All right, let's get back to our slides here. And just want to talk about clustering. Before getting into clustering, there's one more thing I forgot to talk about the final projects. Just want to make sure because everyone is here right now. So for next week, which is week 7, I was planning to have a guest speaker here, but she's not available for next week. So and she's doing something very cool. She's running a health company, and they're doing like a lot of these data mining stuff on health data. So I think it's a very interesting topic to hear about, and how she started with the startup and where they are right now. And so there's a lot of cool info on it. So I think it's going to be really cool to have her here. But she's not able to make it next week. But she can do it on March 2nd, which is our last week, week 8. And her presentation is like for half an hour. But since we're going to be doing the final presentations on the last week, we're probably going to run out of time. Now, one suggestion I have is if anyone is will be willing to do their final presentation next week, at least 3 teams, so we can save half an hour from week 8. That would be great. I mean, is there anyone that feels like they can prepare their final presentation for next week? No one? There's definitely going to be a bonus. I mean, for whoever does that. Obviously, right? All right, no worries. Just let me know. I mean, if you just let me know by email, we will coordinate this. Okay? I mean, please, let's see if we can do it next week. It's what? Oh, start the class half an hour early? Well, it depends on your schedules. All right, is everyone able to start their class around like 6:30? Yeah? 6:30? 6:30, right? We always start at 7, so 6:30. All right, let's.
Yeah, 7 to 9:30.
We will communicate through email, okay? And see what we can do for next week. All right, let's continue to another topic. It's called clustering. This is again to be honest, it's an important topic, but not super useful. It's not as useful as classification and regression. I mean, I promise. Even though, again, it's an important topic in data science and machine learning. Everyone talks about clustering, but it's not that much applicable. You'll see why. Like, here's a formal definition I put up here for clustering. It's the process of organizing objects into groups which those members are similar somehow. Okay? For example, this simple plot here, just by looking by eye, you can guess that, okay, I have 4 separate clusters, for example. Okay? It's just a general definition about it. I put up a lot of more slides for this. You just want to revisit the last example we talked about, remember, for classification, if you remember this data set. What was it called? Iris? The Iris data set. We used petal.length and cpal.length to plot these data points, remember? And we used the color parameter to define the species of these data points. Is that correct? Okay. Now, this column, which is called species, is a label for these data points. How about if our data set was like this? So if you remove the species, how is the data going to look like? We're not going to have any colors anymore, right? We don't know what the species are. Is that correct? All right. So this is unlabeled data. If we call the species as a label, This is unlabeled because we do not have any information about the species at this point. But visually, we can see that this seems like a cluster, this seems like another cluster, and this seems, or you can also consider this whole thing as a cluster, right? It's not really obvious that that part of the data is like two clusters. Now, what does this mean? This is like one single cluster. It means that all of these data points here have something in common. And what is that? The species. The type, the species type, is most likely similar for these objects, and these objects, and these objects, for example. And here comes the problem of clustering. We want to figure out some separate clusters that can show, again, a bunch of these data points that have a similar feature, or they're kind of similar, for example, in species here. And it brings up to the topic of clustering. We're going to see some examples, and I'm just going to run some R code on clustering to see how it works, okay? There's, again, tons of methods for clustering, similar to classification. Remember, we talked about, like we said, there's at least 100 models for doing classification. The same thing for clustering. At least this is a list of well-known methods. But the first 4 are the most useful ones, at least based on my personal experience. I mean, I've used these 4 methods in a lot of projects. Okay? And the simplest one is k-means. So that's why we're going to go and dig through k-means and see how it works in detail. Okay? But we cannot do it for the rest of the methods. We're going to be talking about k-means and see how it exactly works, and then we'll see how you can write the code in R. And then again, similar to classification, you can replace the method of k-means by any of these methods and see how the clustering works. Okay? All right, let's talk about k-means. Here's the algorithm. There's like 5 steps in the algorithm for finding separate clusters. Now, first of all, it's called k-means. The k stands for the number of clusters. How can we find the number of clusters? We'll talk about it later. Okay? But on the first step, just by visually looking at the data, we can guess there's probably 3 clusters, right? And we want to find those 3 clusters. We just want to see like which data points belong to the same cluster. That's the problem of clustering. Even though we're not sure like how they're similar to each other, is it in terms of like, I don't know, like their color, their species, their whatever. We have no idea. We just know that they're similar in this 2-dimensional plot. Now, this is how it works. Based on k, let's set it up to 3. We're going to throw 3 random dots onto the plot, anywhere. The next step is, by looking at the closest neighbors to every data point, we will define the cluster members. So for example, if this is cluster 1, 2, and 3, okay, we're going to spread them out. I mean, we're going to spread these 3 data points out on the plane. And according to nearest neighbor, we will give the same label to all of those nearest dots. Okay, I'll show you in a visual example in the next slides. And then we're going to we'll estimate the centroid, the centroid part of the cluster, which I'll talk about what it is. So centroid is like the middle, the data point that represents the whole cluster. And we're just going to repeat this over and over. I'm just going to show you an example. I think just talking about the algorithm is not very useful. Let's go with this example. All right. Let's say we have all these data points, these square data points here, and we want to find like 3 separate clusters. We're going to throw like 3 dots, K1, K2, and K3 as the centroids of the 3 clusters. Okay? Now, the next step is to give the same label to all of those data points that are closer to each of these data points, right? So we have like K1 and K2 and K3. These green data points are closer to K1, so we're going to give them green. They belong to the cluster, which K1 is the representer here. And again, the same data points here, we're going to give them a colored red, which are closer to K2. And these data points are closer to K3, so we're going to give them orange here. Right? Okay. So at this point, we have like 3 separate clusters in the first step. What are we going to do next? Well, since we have new clusters, we're going to recalculate those centroids. Okay. What is centroid again? Centroid is like some data point that has the least sum of distance to all of the data points in that cluster. How can we calculate it? By averaging those data points in one cluster. For example, here we have x and y, right? So for finding the new centroid of this cluster, what we're going to do is we're going to average all of the x's of these data points and all of the y's. It's going to give us a new x and y, which is the centroid, the x and y for the centroid data point, right? Is that clear?
You said it was the least sum of distance.
Distances, yeah, to that data point. So for example, we just want to find some data point here that has the least sum of distance to all of the data points in that cluster. In other words, we want to average them. We want to average their x and y's in this example. Is that correct? All right, so let's do this. What will happen? These data points, which were the centroids at the beginning, will move. See? So we're going to get like a new centroid for this green cluster, a new one for the orange one, and the new one for the red one. Now we're going to repeat this again. We're going to assign colors to, again, according to nearest neighbor. We'll find the closest neighbors to every data point and give them the label, okay? So some of the labels are going to change. For example, look at this green data point. This one belonged to this green cluster before. But with this rearrangement of these clusters and the centroids, now which cluster should it belong to? The red one, for example. Let's assume that this distance here is less than this distance, right? So the closest neighbor to that green dot is the red cluster. Is that correct? All right, see what happens in the next step. Just look at this data point. Turns red. And maybe some other data points change their label. All right, what are we going to do next? We're going to do it again. We're going to calculate the centers because our clusters changed. Right? I mean, right now we just added a new data point to the red cluster. So the centroid, the central data point, will move. So again, we're going to do the same thing. We're going to calculate the average of all these red data points and calculate the new centroid. We're going to calculate the average of these guys and move the new and the centroid to the new data point. The same thing for the green one. Okay? Here we go. What should we do next? We're going to repeat it again. We're going to look for every data point and find its closest centroid and give it the same label until nothing changes. Exactly. That's when the clusters become stable. Is that correct? All right. Well, these are some GIF images. I have to go to full screen in order to show these guys how they move. But if I go to full screen, this recording is going to stop. Should I go to full screen or not? What? You can just imagine, like, these guys are moving, okay? Or I can maybe show them. I can just send you an email. But these GIF images here will show, like, how these centroids move and how the cluster colors can change until it becomes stable. So at one, no, if we stop the recording, it's almost impossible to resume it. I've tried it, before it, so it's a lot of pain. Okay.
Cluster on non-numerical variables.
Well, again, you have to find features for those data points and assign them values. There's no other way you can do that. You have to have numbers in order to define them clusters. Or even if you have labels and tags, you can still calculate the distance by looking at how many labels are the same, and you can, for example, if you remember Hamming distance that we talked about, similarity between texts. text or like strings, you can use some sort of metrics like that. The clustering is usually defined between like in numerical data. It's usually, yeah.
So isn't the accuracy of this sort of predicated on having the right number
Of K.
K?
Exactly. Yes, that's right. Now the big question here is what? What is the right number of K? All right, we're going to talk about it.
I have another question for you. So
Sure.
why is it the average of the distances as opposed to the squares?
Uh,
So wouldn't we want to do that for something with negative values? Like that one, right?
what's your question again? One more time.
So ordinary these squares,
Yeah.
squaring for those obviously as we talked about last time. But
Yeah.
this you're saying is not squared? This is
I
just
think
like
it's
the
not
average.
squared, yeah. I think it's not. Yeah, it's just like just averaging those data points. I mean, you can show the math, that averaging those x and y's, for example, in a two-dimensional plot, will give you a data point which has the least, sum of distances between from all of them. Yeah. So it's not squared. I'm sure it's not. It's just like summing up the distance. Just averaging those data points. All right. Another example. Again, this is a GIF image. You will see like these colors are going to move, until they become stable. Now, and of course, in every of these examples, if we're using k-means, k is set up. In this example, k is what? The number of clusters we have here, right? The number of colors we have here. And you're going to see like these colors are going to be moving until it becomes stable, and that's when we get the right clusters. Now, how can we do clustering in R? There's a function called k-means for doing k-means. It's that simple. Now, and the library is called stats. So I'm going to talk. I'll just write the code for you. But again, going back to the same example that we were talking about, the cpal.length and the petal.length here. The question is, we just want to use these, for example, two columns, which are what? cpal.length and petal.length, in order to cluster this data point, these data points, into 3 separate clusters. Now, we're going to be using a package called stats, which includes multiple functions for clustering. And one of those functions that we talked about right now was what k-means. Okay? So you can, if you add this library here, which I'm going to do right now, well, you first have to install that library. So let's do it. I'm going to create a new R script here for, call it clustering with k-means. And what I'm going to do is, I'm just going to load a library called stats. Okay, so before loading the library, you obviously have to go to packages and then install stats, right? I'm just going to load it here. And all right, so library stats. Now the next part is, if you look into the slides, is let's load the iris data set one more time. So iris equal to iris. And I'm just going to load it here. So here we have this data set, remember? We have sepal.length, sepal.width, petal, length, and width, and the species. Now what I'm going to do is, I want to create some clusters called, I'm going to call it like iris cluster, equal, I'm going to use k-means, and the only 2 inputs for k-means is, first of all, what? The data that you want to cluster. What is the data here? Well, iris, which columns? Sepal, yeah, it's like column, what column was it? Column 1 and 3, okay? I think using numbers in this case is simpler than using the names. I mean, the names are pretty long. So we're going to pick column 1 and 3, which you can see those data points here on this plot. And we want to cluster them. So I'm going to pick C1 and 3. And the next input is what? K. What is the number of clusters in this example? 3. Is that correct? All right. So I'm just going to run this line of code and see what happens. Here we go. Let me print iris clusters and see what it is. Iris clusters Well, it's just going to give you some like general information about the clusters, but more precisely, you can write iris clusters, the dollar cluster. It's going to give you what? What are these guys? These are the cluster numbers for every data point. So the input was iris, right? How many rows do we have in iris? We have like 150. All right, here we go. So we got 150 labels, which every label is showing the label of that record, or the cluster number for that record. Now, here's the point. Before this, we had some information like species about those data points. But now, we have cluster numbers, 1, 2, 3. So we know that all of the 1s go together, all of the 2s go together, all of the 3s go together, but we don't know what the species is, obviously, because your data was unlabeled. Okay? Now, let's do something else. Let's do a ggplot here and plot those 2 columns of iris, and then give them colors of these labels, and see if it looks similar to what we had before, which we used species as the color. Remember? Okay? All right, I'm going to do this. So before using ggplot, I'm going to load the library, ggplot2, and here I'm going to do ggplot what? Iris. Which columns? 1 and 3. What's the next input? AES. So I'm going to get, okay, or we can just use iris. And then AES, we're going to give the labels, I'm sorry, which columns we're going to be using? Petal, what was it? Petal.length. So what was the call names of iris? So we're going to be using 1 and 3. So this and this, right? Okay, so I'm just going to pick this guy here and petal.length. Plus, let's forget about the color at this point. Let's just plot it. Geom underline. We want to do a scatter plot, remember? Point, exactly. So if I run this, I'm going to get the same plot that we have in the slides. I'll explain what this is one more time. Size 3, I'm just going to make it a little larger. Okay, so this guy here is what? It's the iris data set showing sepal.length on the x-axis and the petal.length on the y-axis, right? Same data that we had. Using this ggplot function here. So again, if you recall ggplot, the first input was the name of the data set. The second input, which you put inside AES, is the features or the variables that you want to plot. So we want to plot this guy and this guy. And then do a scatter plot. Geom underline point, exactly. So we're going to do a scatter plot. So this is how the data looks like. Now, in this case, we're assuming that we do not know what the species are. So we don't really know what the exact labels of those data sets are. The only information that we have right now after doing clustering is the cluster labels of those data points, right? Inside iris, what was it? Clusters? Iris clusters. So what I'm going to do right now is I'm going to give a color to each of these data points, showing their cluster number. How can I do that? Inside AES, I'm going to use exactly. I'm going to do color equal to. Let me go to the next line so you can see what's going on here. Color iris clusters. Is this going to work? Very good. Okay, let me fix this. It's not enough space here. All right. Good point. Dollar clusters. So this is basically the labels of the clusters, 1, 2, and 3. If I run this, let's see what happens. What happened? Must be either length 1 or the same as the data. Does anyone know what the problem is here?
Oh, it's a cluster WS.
This one?
Yeah.
Oh, okay. Just cluster, got it. All right, exactly. What happened? We gave colors to these clusters. Why is it looking like this? Why we're getting like a spectrum of colors? Exactly. Because those labels are continuous values. They're number 1, number 2, number 3. If we change them to label 1 or string 1 or character 1, 2, and 3, we're going to get like categorical colors, right? Let's simply do that. We're just going to change what? Exactly. As dot character or as dot factor. I'm just going to put an as dot character here for this guy. We don't really have enough space here. Yeah. Oop. Okay. Well, anyway, let me run this guy here. And here we go. So we got like 3 discrete colors. We got 3 categories. 1, 2, and 3. Now this data set looks very similar to the one that we did the scatter plot using the species, right? So this is showing that we did a good job. I mean, the clustering method was able to separate those 3 clusters pretty well. Right? Right. Is everything clear about the code and how k-means work? The next step is going to be how can we evaluate a clustering and see, like, say how good is a clustering. Okay, that's going to be the next step.
How did you do the 3 clusters?
Yeah, that's what we're going to talk about. So if we can come up with some kind of metric to show the goodness of our clustering, we can try different Ks and pick the best one. Is that correct? Yes, it is. All right. Just going to go back to the slides. Any questions? All right, we talked about this. This is the same plot we did right now. Okay? Gave colors based on their cluster labels. Here it is. Now, in order to measure the goodness of a clustering and how separate those clusters are, there are at least 5 to 10, I think, metrics and methods. The simplest one, again, and the most common one, is called this guy here, SSE. It's called sum of squared error. What it is, the intuition is, we're looking for a clustering which has the less variation in each cluster. That's the best clustering. Okay? Now, what we want to do next is, we want to be able to calculate SSE and R and figure out the best number of cluster. Now, in general, if we increase the number of clusters, what do you think will happen to SSE? Is it going to go down or is it going to go up? It's going to go down, exactly. So for example, if we have like n data points and we cluster it by n clusters, it's going to be the best SSE ever because like every data point is representing one cluster. But this is not practical. I mean, it's not a good cluster. We'll talk about it right now.
You said clusters. Do you mean centroid?
Centers, yes, exactly, yes. So, variations among to the centroids, or in other words, like we're looking for like pretty dense and close clusters and clusters that have data points close to the centroids. Okay, that's what we're looking for. That's the goal. Now, how can we do that? I'm not going to go through this code here because it has some loops, and I'm afraid people are going to say that this is not an R programming class, right? But you can copy this code and just put it in R, and it will give you this plot here. I'm going to do that, okay? I'm not even going to read what this data is. So what I'm going to do is, this my data here is basically the data that we want to cluster, okay? So I assign iris, which columns? 1 and 3, right? All right, let's go back to our code. I'm just going to put this guy here. Let me create a new, well, not a new. I can do it here. So we want to do some evaluate the clusters. Okay, I'm gonna put the code here. Just make sure that you remove these signs here. It's not part of the code. In general, I can tell you what this code is doing. It's assigning k, the number of clusters, from, for example, 1 to 15 or 2 to 15. And every time it's calculating SSE. And then it's plotting it. That's what this code is doing, okay? Now, let's run this guy and see what happens. Oops. All right, what's the problem here? This guy worked. What's the problem? It's what? Central. This guy? Equal to I. Oh, what is this plus? Yeah, we don't need this plus here. Okay, here we go. All right, just be careful when you copy paste the code. Oops. Unexpected plot this. Why? Okay. Again, we have O. We have another plus here. Okay, so it's always not a good idea to copy paste the code. Figure margin's too large. All right, I'm gonna skip this. But anyway, if you run this code, you'll get this plot. I mean, I just got it like before the class. Okay, I just ran this code and I got this. What this plot is showing is, so I mean the error. I know what the error is in R. I mean, just don't want to waste your time. This is giving you like pretty big margins for because I've done like a lot of plots before. So that's why if I restart R, this problem will go away. But anyway, you're gonna get this plot. What is this plot showing? The plot is showing on the x-axis the number of clusters, k. And on the y-axis, it's showing SSEs. So we're looking for lower SSEs, right? Okay, so should we pick like k equal to 14? No. We're always going to find the elbow of this plot, which is around like 3, 4, right? So the best number of clusters is either 3 or 4 in this example. Now this is one of the methods, okay? There's like at least 10 other methods for finding the best number of clusters. Any questions on this method one? This one? Is it clear? All right, let's get into another term that you've definitely heard a lot, supervised and unsupervised. So at this point, we know what regression is, we know what classification is, we know what clustering is, and now we just want to define two terms that people use a lot in the community. They use supervised and unsupervised methods. So supervised methods are, or supervised learning, is any method in machine learning that uses labeled data. Example, regression, classification. Unsupervised methods or unsupervised learning are any methods that do not have labeled data. Clustering. We also have semi-supervised learning, which we'll talk about later maybe if we have time. Okay, it's just a general term, it's not really something significant, yeah.
In k-means, can I control the starting point of the data point?
Yes, you can. It's one of the parameters. That's a good point. So for k-means, we started with like 3, for example, for k equal to 3, we started with 3 random dots, random points. The question is, can we control them? Yes, that's possible. But usually what k-means does is it will randomly select 3 data points and it'll repeat this multiple times to come up with the best cluster. That's what happens, okay? So even if like k is equal to 3, but it still depends on how you throw those dots on the plane, right? And it will do this multiple times, and it's going to pick the one with the lowest SSE. All right, let's get into association rule mining. I think this is the most interesting, exciting, and simplest. It's super simple. You'll see why. Topic in data mining and machine learning. It's widely used, and you'll see tons of examples of association rule mining, what is it? It's a very, very useful topic. I mean, it's almost applied to any project. I mean, whatever project that we start working on, one of our first steps is to apply association rule mining and find some associations. We're going to talk about what it is. There's a term called market basket analysis that you've probably heard of. What this topic is about is, in general, if a customer goes to a store and buys, for example, bananas, what are the other items that you can recommend to the customer? For example, customers who bought banana also bought these items here, right? This is called market basket analysis. Now, what we want to do is we want to introduce a method in data mining which can find these associations for us. For example, we're going to give the whole data set of like customers, what they bought, or all of their transactions into this model, into this method. This method is going to tell us that, for example, 90% of the customers who bought banana also bought these items, okay? So all of the recommender systems are based on this algorithm, obviously. You can simply see why. These are some real examples from the market. So what people did was they let's say like millions of transactions from supermarkets. They dump in the data into this method, and this method was able to find these associations. And this is based on true data. It's not made up. Most of the customers who bought onions and potatoes bought burgers as well. It's kind of intuitive, right? Isn't it? This is also a very good way if you want to find an item. I went to Costco once. I wasn't able to find potatoes, but I found burgers and onions. So I was sure that I can find potatoes there, and I was right. But it was right there. So a lot of these marketers use this kind of information for setting up their store. Okay, so they don't want the customers to waste their time looking around for all of these items. They know that whoever buys these two items is probably going to buy this one as well. So they're going to put these three items close to each other. Okay? Here's another one. If someone buys flour and sugar, they will most likely buy egg. They probably want to bake a cake. That's right? Now this one is not really intuitive. Most of the customers who bought diapers and milk also bought Coke, not Pepsi, Coke. Okay? Why? We don't know why. This is what the data is showing, okay? And there's maybe probably no justification for it. There's no reason. It could be, yeah. It may be. Oh, I see, okay. Yeah.
By the same company.
By the same company, it could be, yeah. Definitely, yeah. So this comes. And this one is just a joke. All right, now there are some terms in association rule mining we're going to talk about, and then we'll get into, again, how to code this in R. And, well, one of the useful terms is called items. So items is basically, the objects that we're looking into their correlations. In a market basket analysis example, items are, like what? Items are merchandises, or these like onion, potato, whatever that we're looking at. Okay, these are called items, right? Now, we have something else called transactions. What is transactions? Transaction is a set of items that come together. So for example, every purchase or every transaction of a customer is like a set of items that they put in their basket and they bought all together, right? That's called transactions. So it's like a set of items. And finally, rules is the output of our algorithm. It's the output of association rule mining, which is going to give us like a set of rules looking like this. Having an LHS means left-hand side, very simple, and right-hand side. So this means that these items that were, if some customer purchased these items together, they most likely purchase this one as well. Is that right? So this is how the rules are going to look like. Now this can be like multiple items. It can be one item. This one can be one item. It can be multiple items. You can easily expand the algorithm. So for example, if any customer buys item 1 and 2, they will most likely buy item 4 and 5 and 6 and 7. That's possible. You can easily expand it, okay? Now, there's some metrics that is very useful in this algorithm. One of them is called support, and one of them is called confidence. Let's first talk about confidence, which is simpler. You can easily guess what it is, right? What is the confidence of the rule? Like how many customers who bought onions and potatoes bought burgers as well? That's confidence. Like you can say like 90% confidence.
Would you say that's different than the likelihood portion of it?
No, it's pretty the same, right?
Well, I mean like,
You mean like, oh, how many times this transaction happened, you mean?
yeah.
Yeah, so that is support.
Okay.
That's what support is. So here's the main point. By just looking at confidence, you can never say if a rule is good or not. Why?
Maybe
Because
a one
the
transaction.
threshold data might be too small.
Exactly. Just imagine like if one customer bought some items together, right? What is the confidence? It's 100%. Because any customer that bought X and Y bought Z, but it was only one customer. So even though the confidence score is high, but we don't care about that rule. So along confidence, we have something else called support. So support means what percentage, what portion of all of the transactions included that rule. For example, like what portion of the customers did buy onion, tomatoes, and burgers? So both of these metrics are important for us. We're going to be looking at both of them at the same time in order to distinguish a good rule from a bad rule. Now, what are the algorithms in order to find these associations between these items? Again, there are multiple algorithms, just put up some of here, but the most famous one is called a priori. A priori is it definitely is the most effective, fastest, optimal metric algorithm that is used for association rule mining, okay? So whenever you talk about association rule mining, just stick to this method, a priori. It's the most common one. If you just type in association rule mining, the first search result is going to come up like a priori method, okay? How does it work? We don't care, right? We're just going to be using this algorithm in order to figure out some associations. Now, I just put up 2 links here. I think they're very nice tutorials. And they're just going to show you like some very nice training examples, which you can load in R and then run this method, this a priori method, and find the associations between the items, okay? So I'm going to skip this part. I mean, you can do it yourself. I've done it multiple times. It's very, I think, clear and easy to follow, okay? You can go through these 2 links. If you have any questions, just let me know. Here's a touching story on association rule mining. Probably heard about it, maybe. It's a story about Target. Some years ago, Target, some guy just went into Target and was looking for the supervisor and was complaining and shouting and saying that, what do you guys think about my family? Why do you guys are like sending coupons about pregnancy to my house? I have like a 12-year daughter, and why do you guys think that she's pregnant? Okay, so that and this was and the supervisor and the manager of the store were like so embarrassed and apologized and said, we are so sorry, this will never happen again. They gave this guy like a lot of coupons to satisfy him and blah blah blah. And then what happened was this manager called in later to apologize again. And the dad just answered the phone and said that, oh, I'm sorry, you were right. My daughter was pregnant. And I had no idea about it. Now, how this worked was, there was an algorithm, association rule method, applied on Target, which was able to detect if someone purchases like 19 or 20 items is pregnant. And based on that, they were able to figure out like who are the pregnant people, and they would send them just some coupons, coupons for diapers and whatever to them. So this is again a true story, and you can look into this article. It's not like made up. It's absolutely true. So this is the power of association rule mining. It's very useful. It's a very, very useful method. Next part, we're going to get into this real-world application, this health insurance project that just wanted to talk about. I'm going to go through this pretty quick, not much details, but I think it's really interesting. I mean, I personally have spent so much time on this project because I love it. I simply love it. And I'll give you some info. So this data set includes 1 billion prescriptions over 5 years for patients in another country, not the US. Okay? Now, the data set includes the drug name. I mean, just put this for like a brief representation of the data set. And it obviously includes a lot of other features. But these are some of the useful features that we're going to talk about. Okay? Drug, what is the drug name in the prescription? The province or the town, the city name that drug was prescribed, the gender, and the date. I'm just going to show you some simple examples that we ran on this data set, and then using some of these methods, I'm going to show you some of the real results on the data. Now, the first thing about this data, the beauty of this data is there's no exact spread of diseases around the country, right? I mean, there's no really good database for finding out like what kind of disease is spread out like in different parts of the country. But there's exact and accurate data for prescriptions because these insurance companies record all of this data on their databases, right? All right. So how about if we are able to somehow build a model which can input the prescription and predict the disease with a very high accuracy? What's going to happen? Well, we can simply figure out the spread of diseases all around the country in different dates and different seasons, in different cities, in different places, and different genders. Right? And we did it. I mean, we use a method, it's a very simple method. We use a ground truth of like a database showing like what is every drug used for, what is the section and what is the subsection for, like what kind of disease it's used for, okay? And we built a nearest neighbor model classifier, which was able to look into the prescription and then pick every drug, look into the causes, look into the sections and subsections related to that drug, and then based on majority voting or nearest neighbor, it will tell you that, okay, what kind of disease that prescription belongs to. And here's a set of examples, just want to show you. So on the left-hand side, this column here is like a bunch of prescriptions, right? Some of them include only one drug. Some of them have like multiple drugs in it. And this section is the output of our model that was able to define and predict the disease and what the problem was according to that patient. So for example, I mean, these two cases were very simple because it's only one drug and it's specifically used in cancer. Okay? But for like the ones that have multiple drugs, it's not that easy. I mean, you have to look into that whole like ground truth, count which one is like for the different sections and different subsections and figure it out. Anyway, and then we came up with some probabilities and just to show like how probable it is. And we showed these results. So the only way to verify this is what? To show the results to an expert, right? Because we don't really have actual labels. We don't have real labels of this data to tell us like what are the exact diseases for those prescriptions. So what we did, we ran this for like 10,000 prescriptions and sent them to some expert, and they were really impressed by the results. I mean, they said like most of these predictions were correct based on that, okay? And we still have a long way to go, and there's a lot of things that we have to trigger and make this more accurate, make the model more accurate. For example, one of the features that we want to add is looking into the history of some patient, okay? And that is going to add as a feature, because if someone has cancer, or if, for example, if a drug is used for both, for example, cancer and let's say like some skin problems, but if we look into the record and see that this guy had cancer last year, well, we can predict that this prescription was definitely for cancer. Okay? And there's like tons of other information that we can add to get more accurate results. The next thing we did, I don't want to get into too much details, but the next thing we did, because we talked about this associative mining, we applied this on the data and see what we got. So first of all, going back to the items and the transactions, remember? We talked about these definitions. So in this project, what are the items? Drugs. What are the transactions? Prescriptions. Because they're a set of drugs that come together for one patient. And what are the rules? Well, here are the rules. So we ran this on like 10 million records of data, and we found that, for example, with 92% accuracy, if this drug and this, which I have no idea what they are, if they come together in a prescription, with 92% accuracy, you will also see this one in the prescription. Or if you see these guys, with 100% accuracy, you will see this guy as well. Now, why is this useful? Well, it could be useful in a lot of ways. First of all, it can give like some sort of suggestion to the doctor. If the doctor is like prescribing like drug 1 and drug 2, this rule can fire and say that, oh, drug 3 should also be prescribed, most likely. It can just like give some suggestion to the doctor. That's one of the things, you know. There's a lot of other things that we can find. Another set of results that I didn't put up here is we ran this on not only drugs, on even like the cities, the provinces, and the gender. And we were able to find some associations between the gender, the drug, and the province, for example. Question?
Could this also be used, for example, to find a negative effect? Like, if these two drugs are being prescribed, this third one is likely to be prescribed, and there's like negative connotations saying that if they're all prescribed together or something, that something else is going on? Like drug reaction?
That's a very good point, yes. That's also definitely possible. Or for example, we can apply this for like fraud detection. Not exactly fraud detection, but let's say in this case, 97%. Okay? You can look into those the 3% that this didn't happen. And look into the reason and investigate it. Why in 3% of the cases it didn't happen? Because this seems like a rule. It's like pretty confident. So you can look into the 3% which had these two items in the prescription, but didn't have this one. Why? Well, you can do some sort of investigation. So a lot of times, yes, you can look for some like some items like that. I mean, it's
So
like
is
another.
this like a tool for pattern recognition?
It is, yes, obvious. Obvious. It's one of the tools used.
What's the use case for this one?
What is it?
Like what, I mean, like how is this useful, knowing this stuff?
You mean these rules, right? Or-
I mean, in the case of like prescription and knowing like what goes with what.
Yeah.
You know.
To be honest, we're not really sure at this point, and we just found out these associations. But I think finding the associations between the drugs themselves, only the drugs, can be useful, as I said, for example, giving recommendations to the doctor. I mean, if the doctor is prescribing drug 1 and drug 2, our system can tell that, okay, all of the prescriptions that had like drug 1 and drug 2, they also had 3. Okay, so this is one. But another useful thing is that if you put like some other information here, like some other features, it can find some associations between like, drugs and some specific, circumstances.
I would
Or
say
like
that
the name of the city or.
pharmacies use it now because, like, if you go into a pharmacy and you
Yeah.
try and buy something like pseudoephedrine and some nail polish remover,
Yeah.
something comes up and says, "Whoa, whoa!" Like,
Exactly.
go
This
check
is
your
against the
ID.
rules. Yeah.
Right.
Exactly. That definitely happens. Or it can easily like cover up human error. You know, if like the pharmacist is putting two things wrong in just like one bag, if they scan it, our system can just pop up and say, oh, these two drugs shouldn't go together. Something's wrong. So it could be I think effective and useful in a lot of ways.
Yeah. Manage the inventory.
What?
Those support numbers look pretty low. How do you interpret those?
Even though they're low, because the data set is very big, like this number is like almost like 400 prescriptions. I mean, this number times 10 million is like 400 prescriptions. It's a lot. It's still a lot. Because the size of the data is so big and the number of unique drugs is so high, that's why these numbers are definitely going to be low, of course. Because not many cases these kind of combinations are going to happen, especially for some, like for cancer and some unique, diseases. Well, of course, the support score is not going to be that high. Question?
I was just adding to your point.
Yeah.
Manage the inventory based on diseases.
Exactly, yes. I'll talk about that as well. And here are the next steps that we're going to take in this project. So any advice, if you have any idea about it, I mean, that would be really appreciated. These are the 4 steps that we want to take for the next step. Number 1, we want to predict the demand for drugs in each province for the next 6 months. So that if someone has diabetes, doesn't have to wait for the drug for like 2 weeks or 2 months, right? I'm especially talking about small provinces and small towns, okay? I mean, like big cities, of course, you can easily find any drug you want. But in some of these like small cities around the country, you see like a lot of people that have heart issues, and they're not able to get their drug because that drug doesn't exist in that state, okay? So we can look into this trend of like 5 years of data and predict what's going to happen, what is going to be the demand for the next 6 months. We did a very similar project for Bosch Research in Palo Alto, the German company you're probably aware of. These guys, their revenue is like 60% from auto parts, okay? So they build like from auto parts, Bosch, the German company.
Yeah.
Their main revenue source is from manufacturing auto parts.
Did you
So
show us
like,
that like week 1 or week 2?
I think I did, yes, exactly. So what I want to say is the project that was done there was looking at, for example, for I think 40,000 auto parts, predicting what is the demand for each of these parts in the next 6 months. Similar here. Just replace those auto parts with drugs. You can do the same thing. This is number 1. Number 2, we want to discover correlations between diseases and some geographical causes or roots that can cause those diseases, and we can come up with some very simple hints that, for example, if whatever, let's say disease X is like a lot in some part of the country, and the water is polluted in that area, well, that disease can be correlated to the pollution of water. So the government could go and do something and fix it. Yeah.
Yeah, speaking of medication, so I feel like in the US, a lot of the medications are being pushed because of advertising.
Yeah, I agree.
That's like another factor. Like, what if like there's like a mainstream prescriptions
Yeah.
only because of advertising? So
You can
I see.
only really look at that like post 1993 when the law changed about advertising and stuff. You couldn't really, there's only so much historic data because they didn't change the laws involving advertisements in the US until that time. You're looking at different countries, different data depending on the law for advertisements and prescriptions.
That's a good point. Yeah, I agree with you. Yeah, that's a very good point. But at least in this country, I mean, I haven't really seen any advertisements on health data. Yeah, so pretty confident about this one. But and finally, something very simple is after we label all of these prescriptions with those diseases, we can come up with a very simple heat map. Remember heat maps? To show the spread of either drugs or diseases around the country with one simple plot. This is going to be very effective. For example, this part of the country and this part of the country has a lot of cancer has been identified based on our data. For example, it's just an example. I just put it. This is one of the next steps we want to take. I don't really have any results on this one yet. But there's like tons of things you can do. If you come up with any idea on this data set, I mean, it's a pretty simple data set. I mean, those 4 or 5 features that I showed you are the main information in the data set that we use. So if you come up with anything, please let me know. This project is in progress. It's going to take a while. I mean, it's not easy. There's a lot of challenges still at this point.
What are the biggest challenges?
One of the biggest challenges was that the experts were not collaborating with us.
Oh.
So like the first step, what we were doing, well, the easiest way to label these prescriptions was if some experts could like label a couple thousand of these prescriptions and give it to us, we could build a model that could automatically learn what is every prescription, what is the disease for every prescription, like what kind of combination of drugs have come together is going to cause like disease, whatever. Okay, they didn't do this for us. Okay, so what we had to do was we just had to use the internet and use a database of drugs to come up with that ground truth that I showed you. So we had to pull out all of the data. I mean, that was like a lot of pain. Pull out all of this data, and then use a nearest neighbor model to do this. And the main reason we did this was because we wanted to impress those experts so that they will collaborate with us in the next steps. And that's what happened. I mean, we just reached our goal. So we made these results, we made these labels, sent them to these guys, and they couldn't believe that these 10,000 labels were made by a machine, not a human, not by an expert. So they're collaborating very well right now at this point. Yeah. All right, let's get into the next part. Is it too late right now or not? It's 9. Can we continue for like 15 minutes and finish this part or not? Does anyone want to leave the class or? No one? It's okay. I mean, if you raise your hand. All right, let's do this. This is the final topic tonight. And for the LabWorks, I think it's pretty clear. I mean, you can go step by step and just let me know if you have any questions about the LabWorks. All right, we're gonna get to this part. It's a very fun, I think, section here, which is web scraping. Why? The reason that I put this up here was when I joined my company on day number 1, my manager said like, "Hello, how's it going? Do you know how to code in R?" And I said no. He said, "Okay, your number 1 task in 1 week is to learn how to code in R." All right. Okay. Week number 2, he assigned me a task which required like a lot of data, and I said, "Okay, where's the data?" Well, the data didn't exist. And what I had to do was I had to somehow automatically go and grab the data and put it all together from some multiple databases. So what I had to do was I had to build like a web scraper which could automatically access these like databases on the net, pull out data, and put it all together. So that's one of the motivations for doing this. You will see that we can easily automate a lot of like these web clicks that you have to do manually in R. Okay, so this is one of those another cool features in R. I mean, people were asking on day 1 of this class, why do you want to like teach us R? I mean, why R is useful? Well, this is another reason, right? That you're gonna be loving R, hopefully. If we have time, maybe next week or the week after, I just want to show you like maybe 2 more tools. One of them is called R Shiny. It's a web app in R. It's awesome. I mean, it's very beautiful. You can like do it in like less than an hour. You can build a simple web app, you know, for showing all of those plots and even showing those interactive plots like Plotly. Remember we talked about? You can put them on a web app. Very simple. I mean, we'll see the code. If we get time, we're going to dig into that. I haven't put up slides yet for that, but I'll do so. And one last thing is we may also talk about RMySQL, and see that how you can connect to a MySQL database from R. Again, simply. All of this is like 1 line of code. All of these guys. Okay, even in web scraping, you'll see it. It's not much coding here. All right, so what is web scraping on R? As I mentioned, it's just scraping the web and extracting some data and information out of the web and collect it for doing some data mining tasks, right? There is a term called Selenium. Selenium is a Java-based engine that is used for automating web scraping. So it's not only used in R, obviously. I mean, Selenium itself is like Java-based. It's written in Java. But we're going to be using a package in R which can use that Selenium, which can run that Selenium engine for us. All right, let's do web scraping. Just want to start right now, right away. What we have to do is, especially because we don't have enough time, but you can go through all of these steps one by one. Well, the first thing is that you have to make sure that you have Java installed on your computer. I think most of the people have it, probably. The next part is install R Selenium. This is the package, this is the feature that we want to use in R in order to do web scraping, okay? And finally, this guy here is a function called RSDriver. This is something that was changed. I mean, the reason I had to spend time on this was I put up these slides last quarter for R Selenium, but the problem was during this like past 3-4 months, the developer of the package changed a lot of functions. Okay, so when I tried to run the code today at work, I ran into errors. The code was not working. So I had to go through the manual again and figure out what are the new functions that are defined by the developer. This was pretty painful, and the reason was because we're using an open source product. That's the reason. So because this R Selenium is dependent on one guy on the other side of the world that has developed this, right? He can make any changes he wants anytime. That's what he did. He's a good guy though, but anyway, it just made, for example, this RS driver is a new function I wasn't aware of. If you run this function, RS driver, after loading R Selenium, what's going to happen is it will download Selenium, the Java file, the jar file, and put it inside the libraries of R. Okay, so you don't need to worry about anything. Just run RS driver. That's it. That's what it's going to do. And also, this function is going to run the Selenium standalone engine, and it's going to be ready for web scraping. I'm just going to do the same thing that I mentioned right now on my Mac. Okay, and we want to, do something real. We just want to go and scrape like some information out of Google and see if it works, okay? So I'm just gonna open up this guy here. So I'm gonna do web scraping in R using R Selenium. Please make sure that you load R Selenium at the beginning, and just make sure that just gonna remove all of these guys here. So first you have to go to packages again, install R Selenium. Right, that's the first step, and then load the package R Selenium, and then if we go back to our slides, and here's a complete tutorial on how to use R Selenium. Okay, you can find like tons of details here. This is how I learned myself. I just went through this tutorial and figured out how to use R Selenium in different cases and how to like pull out data and navigate through the web and everything. Okay. But right now we're just going to run some examples and see how it works. All right, so the first thing is we're going to load the library R Selenium. The next thing is I'm just going to copy this code here and then explain what it is, okay? So this guy here this is the first step. When you run this function RS driver, as I mentioned, if you run it for the first time, it will take maybe a minute to run because it's downloading that jar file, the Selenium file, and running it for you, okay? For the first time, it's going to take you a minute. But if I do it right now, because I've done it before, it's pretty fast. Now, what this guy is going to do is, it will open a browser in Chrome. Can we change the browser? Of course we can, okay? The default is Chrome, and we're going to use Chrome for some reason I'll mention. So it's going to open it and set this port number here. Sometimes you're going to get an error and say that this port number is being used on your computer. So you can easily change that number, right? That's why I put it here. You can also ignore this. The default is 4444. Anyway, I'm going to run this and see what happens, okay? Oops, I forgot to load the library. And then run this guy here. See, it's running, right? SSL connection error. Probably not connected to it maybe, yeah. Where's my Wi-Fi? Interesting. Settings here. Network. Stanford visitor, but it's not connected, right? This is weird. Let me